Lillian Wang's blog explains that diffusion models are inspired by non-equilibrium thermodynamics. They define a Markov chain. This chain is a series of small, incremental changes.
So like a sequence of events where each step only depends on the one just before it? That's what Markov chain means, right?
Precisely. In the forward process, we slowly add random noise to data. We start with a clean image, x0, and gradually make it noisier over t steps.
So we're taking a clear image and systematically degrading it step by tiny step until it's just pure noise?
Exactly. Imagine an image of a cat. In step 1, we add small amount of Gaussian noise, slightly blurring it. Step 2, a bit more blur and static. We repeat this t times.
Until at step t, our cat image is completely unrecognizable, just a field of random pixels, like television static.
That's x-t. We end up with a sequence of noisy samples, x1 through x-t. The amount of noise added at each step is controlled by a variant schedule, beta t.
So beta t dictates how much degradation happens at each stage. Is it always the same amount of noise added?
Not necessarily the same. The blog notes that beta 1 is less than beta 2, less than beta 3, and so on up until beta t is common. We can add more noise later when the image is already very noisy.
Ah, so the noise increase accelerates. When it's already mostly noise, adding a lot more doesn't hurt. But at the beginning, a small amount is critical.
Precisely. And crucially, when t tends to infinity, x of t is equivalent to an isotropic Gaussian distribution, pure, structureless noise.
So we know exactly what the end state is, a Gaussian distribution. That feels important for being able to reverse the process.
This reparameterization trick is crucial for efficient training. It lets us directly calculate any noisy intermediate state x sub t from the clean image x sub 0 and a single sampled noise vector without needing to iterate through all previous steps. Specifically, x sub t equals square root of bar alpha t times x sub 0 plus square root of 1 minus bar alpha t times epsilon, where epsilon is standard Gaussian noise. This means for training, we can just pick a random t, take our clean image, x sub 0, and directly generate a noisy x sub t by adding a single, scaled noise realization.
Meaning we don't have to run all t steps to get to x sub t? We can jump straight there with a formula. That's super important for training.
Correct. This is vital for training efficiency. We can directly generate a noisy version of any image at any level of noise, which is what we'll use to train the reverse process.
So the forward process is deterministic and well-defined. The real challenge then is to learn how to undo it. How do we build a model for that?
That brings us to the reverse process. We want to go from the pure Gaussian noise xt back to a clean image x0. This is where the model learns.
Okay, so the forward process gives us the problem statement. Here's how an image becomes noise. Now, how do we teach a model to reverse that? That sounds tricky.
To reverse, we need to learn to predict the previous, slightly less noisy state, x sub t minus 1, given the current noisy state, x sub t. As the text says, if we can reverse the above process and sample from q of x sub t minus 1 given x sub t, we will be able to recreate the true sample.
So we're building a model that, for any noisy image, tells us what the image looked like just before that last little bit of noise was added?
Exactly. But here's the catch. We cannot easily estimate q of xt minus 1 given xt because it needs to use the entire data set. We don't have ground truth for every intermediate step.
Right, we only have x0 and xt. We need to infer all those steps in between. So what's the trick?
The trick is, we need to learn a model, p theta, to approximate these conditional probabilities. This p theta is our neural network learning to perform the denoising.
So the network learns to predict xt-1 from xt. But what's it actually learning to predict? Is it the clean image directly?
Not directly the clean image. Think of it like this. If you know xt, and you know how much noise was added to get to xt from xt-1, you can just subtract that noise.
So the network is learning to predict the noise itself, not the clean image. That seems counterintuitive.
Exactly. The neural network, p theta, doesn't predict xt-1 directly. Instead, it predicts the noise component epsilon theta of xt, t that was added at time t. Once we have that predicted noise, during the generation, or reverse process, we can use a formula to estimate the mean of the distribution for xt-1. For example, mu theta of xt, t equals 1 over the square root of alpha t times xt minus 1 minus alpha t over the square root of 1 minus alpha bar t times epsilon theta of xt, t. Then, to get xt-1, we sample from a Gaussian centered at this mu theta with a specific known variance. This iterative process, predicting and subtracting noise, gradually reconstructs the image.
Aha! So if the model learns to predict the noise, epsilon t, then we can just subtract that predicted noise from xt to get a cleaner image. The math sounds complex, but the core idea is clear.
Precisely. The network, often a U-net, takes x sub t and t as input and outputs its prediction of epsilon t. The loss term lt is parameterized to minimize the difference between predicted and actual noise.
So the network is trained by showing it noisy images, and it learns to see the noise that was added so it can then remove it. This is like a very sophisticated denoising autoencoder.
You've got it. And interestingly, Ho et al. 2020 found that training the diffusion model works better with a simplified objective compared to the full variational lower bound. This simplification made training more practical and robust without sacrificing generation quality.
A simplified objective means easier training, right? Does it lose anything by being simpler?
Empirically, the simplified objective is LT is equal to E with subscript t, x subscript 0, epsilon of epsilon minus epsilon subscript theta of x subscript t, t square. This means the network is primarily concerned with accurately predicting the noise epsilon at each step, making the training very direct.
So we've gone from complex thermodynamic analogies, just simply training in your own network to predict noise. The elegance is in making it work.
Indeed, while these DDPMs achieve incredible quality, their iterative nature in pixel space can be computationally demanding, especially for high-resolution images.
Ah, so there's a catch. Generating an image one pixel denoising step at a time for hundreds or thousands of steps sounds very slow for big images.
Exactly. This computational cost became a significant limitation, leading researchers to seek more efficient approaches, which brings us to latent diffusion models.
Latent diffusion? Is that like doing the same thing but in a compressed form?
Precisely. The main drawback of the denoising diffusion probabilistic models we've discussed so far, especially with high-resolution image generation, is their computational cost. Each step operates on the full pixel space of the image.
So if you want to generate a 1024 by 1024 image, the neural network processing that noise is dealing with over 1 million values at each of the hundreds of steps. That's a lot of computation.
Exactly. To tackle this, latent diffusion models, or LDMs, introduce a crucial innovation. They perform the diffusion process not on the high-dimensional pixel data directly, but on a lower-dimensional, perceptually meaningful latent space.
A latent space, like how VAEs work, where a complex image is compressed into a smaller abstract representation. So we're diffusing in that compressed space.
You're spot on. LDMs use an autoencoder to first compress the high-dimensional image into a lower-dimensional latent representation. The forward and reverse diffusion processes then happen entirely within this smaller latent space.
So the network learns to denoise this compact representation rather than the full image. And once the latent noise is removed, it's decoded back into a full resolution image.
That's the core idea. By moving the iterative denoising steps to a compressed latent space, LDMs drastically reduce computational complexity and memory requirements. This allows for much faster sampling and enables generation of higher resolution images that were previously infeasible.
So the quality benefits of diffusion models, but now at a practical speed and resolution. That's a huge leap for practical applications.
Absolutely. Furthermore, this latent space is also highly effective for incorporating conditional information. We can guide the generation process using text prompts, class labels, or even other images, all within this compact latent representation.
So this is how we get those incredible text-to-image models where you type a cat riding a skateboard and it generates exactly that. The latent space provides these semantic hooks for guidance.
Precisely. A prime example is Stable Diffusion, which is a latent diffusion model. Its success in generating diverse, high-quality images from text prompts and its relative efficiency compared to pixel-based diffusion models has made it incredibly popular and accessible.
So, from the fundamental idea of reversing noise in a pixel space, we've evolved to highly efficient models operating in abstract latent spaces, unlocking powerful capabilities like creative text-to-image generation. It's a testament to building on core principles.
Indeed, both DDPMs and LDMs are fundamentally latent variable models that learn to map a simple latent distribution, pure noise, to a complex data distribution, images. The shift to a perceptual latent space in LDMs was a crucial step in making diffusion models practical for widespread use.
It's amazing how much mileage you can get out of a seemingly simple idea like add noise, then learn to remove it, and how quickly the field innovates to overcome limitations.